Good evening students, I am Dr. Ganesh Kumar Patel and welcome to Radiation Oncology course. The today's lecture is the lecture number 32 and the subject of today's lecture is the radiation safety part 2. So we'll continue our, as we understand in the previous lecture, the basic philosophy of radiation protection is the justification, optimization and dose limits. So in optimization we understand the importance of LRA and with the example of medical examination. Now we understand how the LRA can be achieved by how it can be achieved. So this is achieved by time, application of time, distance and shielding. We will discuss one by one the importance of these three parameters. Time. So how the time? As time, the importance of time is that it's very simple. Lesser the time you spend near the radioactive source, the lesser the dose you will receive. It's very simple. The lesser the time you spend a time near the radioactive source, lesser the dose you will receive. Now we will understand with an example. Consider a radiographer is performing barium examination under the fluoroscopy and the equipment is on for 3 minutes for each examination. The radiation level at the location of the radiographer is 100 mR per hour. mR per hour is a unit of exposure. We have understand the exposure is the term defined for radiation level in the air medium, and the unit of exposure is Roentgen, and the exposure rate, the unit of exposure rate is Roentgen per hour. So this is the milli-Roentgen per hour. How many such procedure the radiographer can carry out per week? So from this example we can understand that there is one barium examination, and for each examination the equipment is on for 3 minutes. So if the radiation worker is working 8 hours a day in a week, so how many examinations a day he can perform without crossing the dose limit defined for the radiation worker. So there is a dose limit which is defined for the radiation worker as well as for general public. So radiation, the annual equivalent dose limit for radiographer or the radiation worker is permissible weekly dose limit for a radiation worker is 20 millisievert in a year, which is around 200 mR. And how many weeks in a year? There are 50 weeks in a year. So the permitted weekly dose becomes 2000 divided by 50 is around 40 mR per week. So permissible weekly dose limit for a radiation worker is 40 mR. So this is the given we got, and exposure rate at the location of a radiographer is 100 mR per hour. It is 100 mR per hour. We will convert it into a minute because the examination equipment on time is in minute. So we converted this hour into minute by dividing into 60, and the exposure for each examination is for 3 minutes. So we will simply multiply this into 3 minutes. So we will get a 5 mR. So for each exposure the radiation level received is 5 mR. So for each exposure, for each examination, the radiographer is receiving a 5 mR. So the question was that how many exposure is possible, because we know that the maximum weekly dose limit is 40 mR. So we simply has to divide 5 mR. So hence number of procedures that radiographer can complete in a week is 8 mR. So this is the example. You can understand how the role of time is important. So if the radiation level is higher, you need to spend a lesser time to not cross your radiation dose, permissible dose limit. The second example which explains the importance of distance. As radiation follows an inverse square law, like a light. If you will switch on your torch light, you will see that its divergence decreases. As its divergence increases, the intensity reduces. This is the same concept, the inverse square law, applied with the radiation also. As the distance, suppose this is a radioactive source, as the distance increases from the source and a divergence increases from the source, the intensity or the exposure is decreases and the relation with the distance and rate of decrease of exposure is by a factor of square, so that is why it is called the inverse square law. So suppose at a 1 meter your radiation level is 100 mR. So if you will double a distance, means your distance is doubles, so because the relation is like that, exposure, simply exposure is denoted by x, is directly inversely proportional to 1 upon r square. So if r is 1, your 100 mR per hour, if r becomes 2, so 2 square become 4, so your exposure reduces 4 times, so your radiation level becomes 25 mR. So this is the relation between, this is the role of distance with source. So this is called a inverse square law. So we will understand this inverse square law with an example. Suppose an operator is handling a 10 millicurie of iodine 131 source with 30 centimeter tongs. Within how much time, tong is a long shaped needle that you can carry, within how much time the technician will receive the weakly permissible equivalent dose. So suppose a technician, an operator has to handle a 10 millicurie activity of iodine 131 source, so and the weekly permissible dose limit is 40 mR per week, and within that limit how much time or how much safe distance he can handle. So for that we need to understand the formula of exposure. Formula of exposure is simply gamma ray constant into activity upon distance square. Here in this example you got the gamma ray constant for iodine 131 is 2.18 r centimeter square per millicurie, and 1 Roentgen is equal to 1 rad. Okay, and you know the value of activity. Activity is 10 millicurie. Okay, sorry, activity value is 10 millicurie, and you know the gamma ray constant, and you know the r is 30 centimeter. R is 30 centimeter, and our weekly permissible limit is 40 mR. So exposure level at 30 centimeter from 10 millicurie source is simply you need to multiply the gamma ray constant into the activity. Here you have multiply gamma ray constant into the activity, you got 0.024 Roentgen per hour divided by r square. R means 30 centimeter, 30 square, when you divided you got the 24 mR per hour. So allowed time of work is simply divide the permissible dose limit by 24 mR per hour. With this formula, allowed time of work, you will get the 100 minute. So an operator, how much time the technician will receive the weekly, in 100 minutes he will reach to the weekly dose limit of 40 mR. So this is the important example to understand the important role of distance. One more example. What would be the distance required to reduce the radiation level from a 10 millicurie of iridium 190 source to 2 mR per hour? Gamma ray constant has given. Exposure rate at 1 centimeter from 10 millicurie iridium source is provided. So same formula we have to apply. Gamma ray constant into activity exposure divided by r square. Our gamma ray constant is 4.69, activity is the 10 curie, you multiplied this, and this is the Roentgen, you simply convert into, multiply into 1000, because 1 Roentgen is equal to 10 raised to power 3 milli Roentgen. You multiplied this value, you will get 46,900 mR. Now what would be the distance required to reduce the radiation level from 10 millicurie? So you know that if suppose I1 is directly proportional to 1 upon d1 square and I2 is directly proportional to 1 upon d2 square, we know at one point, so how to calculate at second point. So it becomes like x1 d1 square x2 d2 square. So you know the exposure at one point, you know the distance that point, you have to calculate the d2, you have to calculate d2. Here we have given the exposure at a 1 point 49,000 this, at 1 centimeter, you need to find out second distance where your radiation level is 2 mR per hour, means x2 is given exposure. You need to put these values into this formula and you will get a 1.53 meter. So at 1.3 meter, 53 meter, your radiation level will be 2 mR per hour. So this is the example to understand how the time distance works. Now shielding. The important thing is that first we understand the role of time, the second we understand the role of distance, the third important thing is the shielding. Optimization of these three things is required for safe work or safe practice in the field of radiation. Radiation attenuated, how the radiation attenuated with once it enters into a material, whenever the radiation enters into a material, it starts attenuating exponentially like this, and it depends upon the intensity of material. So suppose this is your any attenuating material can be anything like suppose concrete, steel, lead, anything, and this is your incoming intensity, or this is your incoming beam or primary beam, which is denoted by I naught or initial intensity, and this is your attenuator or material. Once it is attenuated, some amount scattered and some amount reaches to the detector, and x is the thickness of a material, and I is called the transmitted photon intensity. So relation becomes like this: IT transmitted, this become transmitted photon intensity, IT become I naught e power minus mu x. Here IT is the transmitted intensity, I naught is the incident intensity, and because I said that there is exponential decay once the radiation enters into the material, and mu is the linear attenuation coefficient, and x is the thickness of a material. As the thickness of material increases, there is a sharper fall of this radiation level. So this is the formula for attenuation in the material. And now we understand which type of material generally used in the radiation protection for the shielding in a radiation field. The most commonly used material is the concrete, then another is a steel, and another is a lead. All materials have a different density, and the role of density is very important. To understand the shielding calculation or shielding concept, we must know the two terms. First term is the half value layer, and another term is the 10th value layer. As I said that whenever the beam passes through a material, it starts attenuating. The degree of attenuation can be understood with the concept of half value layer. The linear attenuation coefficient is defined as the reduction in the radiation intensity per unit path length and is expressed in centimeter inverse. The linear attenuation coefficient is related to the half value layer with this linear this is the half value layer, HVL, we can say that formula is 0.693 upon mu is a linear attenuation coefficient. So this is the relation between a linear attenuation coefficient and half value layer. We have seen that in this figure, where the intensity reduces to 50% value, that depth is called a half value layer. That depth, this is the absorber thickness, that depth of a absorber is a half value layer. So the thickness of material that attenuates the radiation intensity by 50% of its initial value is called HVT or half value layer. The reduction factor offered 1 HVT is 2, and by 2 HVT is 2 by, so simple, it is written as 2 to the power n. In this way, this is the generalized formula of HVT. Hence, the reduction factor offered by an HVT of shielding material is 2 to the power n. For diagnostic X-ray beam energy, HVT of soft tissue ranges from 2.5 to 3 centimeter. Okay. The 10th value layer, there is another interesting term called 10th value layer, which gives the thickness of a material that attenuates the radiation beam intensity by 90% of its initial value. The reduction factor offered by TVT is 10. Here the reduction factor was 1/2 or 1/2 to the power n, depends on number of HVT, and it is given by 10 to the power n and NVT. The TVT and HVT can be related by this relation. TVT is equal to the relation between the linear attenuation coefficient and TVT is 2.303 upon mu. So it becomes, the relation finally becomes TVT becomes 3.32 HVT. So these are the two terms which are generally used in the shielding calculations of radiation installations or for any layouts like a radiotherapy equipment, or it's a nuclear medicine equipment, or it's a diagnostic equipment. These parameters are required to understand for the shielding calculation. Now the most important second thing is the radiation symbols. The radiation symbol is very important because it's an alert for a common person or a general public that the area of risk area and a safe area. So radiation symbol is very important for any facility of radiation. First we will understand the first symbol is the tree. This is the most common symbol which is generally used for radioactive sources. There the symbols have been divided according to their applications. Like symbols have been pasted where there is a use of a radioactive source, and the symbols have been used where there is a no radioactive source. When we say no radioactive source means there is a artificial source like X-rays. X-rays means man-made X-rays, artificial. Okay, so this is a trefoil radiation symbol having a background of yellow and this pink color trefoil. For inner circle of radius R, suppose the inner circle have a radius R, then the inside radius of blades is 1.5 R, then this radius is 1.5 R, and the outer radius means inner radius is 1.5 R and outer radius of the blade is 5 R. So suppose this inner circle have a radius small r, then this inner circle will have a radius of 1.5 R, and this outer circle will radius of radius 5 R. In this proportion, and the blade to blade difference is 60 degree. In this proportion, the radiation symbol is prepared for a radioactive material, and this is another trefoil radiation symbol for radiation hazard. Okay, so both the symbols can be used for the purpose of radiation hazard as an alert. The next important symbol, the inverted triangle with symbol for X-ray machine. This is for all kind of radiation generating equipment. All kind of radiation generating means the radiation equipment which generate X-rays. X-rays are like a switch on off system, means like your ordinary light where you can simply switch on the switch on or on off system. Same is for the radiation generating equipment where beam can be on and off by the switching mechanism. So for such equipment, for such a radiation generating equipment, the symbol is different. This is an inverted triangle which is written over caution X-rays in two languages. One is English common language, and one is the language is the Hindi language, and another is the local language, because India consists of number of states and different states have a different languages. So for local understanding of the symbol, there is a one more option to have written in local language. This should be written here in local language, and inside there is a X-ray tube diagram. So this is the inverted triangle symbol. And this is the very important symbol. This symbol is generally used for sealed sources like a brachytherapy source. For a brachytherapy unit, you must paste this symbol. This symbol is for radiation symbol of a sealed source. This symbol, you can see that background black and red triangle. So this is the symbol for a sealed source. And these symbols are for unsealed sources. These symbols are for unsealed sources. These symbols can be used for unsealed as well as sealed sources, but this is the additional symbol which should be used for sealed sources. So whenever you are using any radiation generating equipment, there is standard format prepared by a regulatory body. That standard format should look like this, where you should write the type of equipment, the name of the model of a machine, and the license obtained from the regulatory body. In our case, it is Atomic Energy Regulatory Board, which is a national body, which we will understand in future lecture. Here you must paste an inverted symbol, and you must paste a symbol for a pregnant woman. This is a very important thing, and every radiation generating equipment on the door, this kind of format symbol should be there, and it should be mentioned like here, like this. Here you have to paste a copy of license. If it is mandatory to paste a copy of license of a radiation generating equipment. Now the important thing is that as we see that we cannot see the radiation, so how we understand a person is exposed to radiation? So that for that purpose we required some device, we required some system. That system we are going to discuss is the personal monitoring service. What is personal monitoring? The person, there are two types of people in the field. One is who are working in a radiation and they called as a radiation worker, and the other people who are not part of a radiation but they are a occasional visitors like a patient or a patient relative. They count in a public. So the people who are working with the radiation equipment or radiation, they required a personal monitoring because they are constantly exposed to equipment or radiation. So for them there is a personal monitoring service. So there are two types of detectors generally used for personal monitoring. The one is called a active type of detectors and another is called a passive type of detectors. Active detectors, I will give example, is the pocket dosimeter. What actually happen in active detectors? Active detectors are the detectors which give you the radiation level or the value of exposed radiation immediately. It gives the immediately. So that is why I call it is active detectors. And the detectors which gives you the exposed radiation amount after certain period of time, that is called a passive detectors. So first we will understand the passive detectors. So the passive detectors which is used generally is the photosensitive film and a thermoluminescence dosimeter. Initially there were the film were used, that we call a film batches were used, but now it becomes obsolete, it becomes a old technology, and the new system came which is called a thermoluminescence dosimeters. These are the personal dosimeters recorded the cumulated radiation dose over a period of use. Personal monitoring is the evaluation of radiation doses received by the personnel working with radiation sources. Proper use of TLD batch is important in order to record the correct dose. First we understand how to wear the TLD batch, how the TLD batch looks like. This is a TLD batch, a simple TLD batch, which you can see that. It is very important to understand how to wear a TLD badge, because most of the times radiation workers don't understand how to wear a TLD badge. Sometimes radiation workers wear a badge above the lead apron, sometimes it below the lead apron. But what is the right way of wearing a TLD badge? TLD badge should be wear at the level of chest, because it's a chest TLD badge, at the level of chest and below the lead apron, because you are going to receive the radiation after the X-rays are passing through, attenuated through your this lead apron. This is the diagram how to wear a TLD badge. Now when to change your TLD card, because it is a passive detectors, your radiation record is monitored quarterly and it has to be changed quarterly, and there is a service provider where you have to send all these exposed TLD cards for getting the dose recorded and measured. They will give a report of amount of radiation you received in particular time. That is a quarterly service. It is a quarterly service. Every quarter you have to send your TLD batch for the measurement. Now what are the radiation detectors? I said that there is a pocket dosimeter. This is a picture of a pocket dosimeter. This is also a monitor, gas filled detector. There are three types of general detectors: gas filled detectors, solid detectors and liquid detectors. These are also main differences of the different types of detectors. Some are ion chamber based detectors, proportional counter, Giger-Muller counters, these are the types of gas filled detectors. Now TLD. TLD is a albedo type of dosimeter, which means they rely on reflection of incident radiation. Albedo dosimeter means which rely on the reflection of incident radiation. The most common material used as a TLD material is phosphor enriched isotope that exhibit high absorption cross section for incident radiation, like 6 lithium fluoride, also called TLD 600. There are number of TLD materials available. Out of that, some we will discuss: 6 lithium fluoride, 7 lithium fluorides, lithium fluoride, and according to the type of material used in that TLD, it has been numbered like TLD 600, 700, TLD 100, TLD 1000, TLD 6000. These TLDs are commonly worn by radiation worker working in nuclear field, working in a nuclear reactors, which we discuss. But most important thing, that's in India, the TLD which we are using and the material which is developed by indigenously by Indian scientists, that is a CaSO4, calcium sulfate with doping of dysprosium, CaSO4 dysprosium. This is known as a TLD 900. It is a highly sensitive phosphor, stands for dysprosium, which is a doped material, and this is commonly used in India and in all the medical field within India, and this material developed by Bhabha Atomic Research Center scientists. So you must remember, in India the TLD material which is used is TLD 900. The material is CaSO4 dysprosium doping. This is the important thing. TLD 500, in Western or European countries, they were using this material TLD 500. The composition of their material was Al2O3, aluminum oxide, Al2O3 with carbon doping, is also highly sensitive material with good thermal stability. This material is commonly used in USA. Recently, new material is developed for personal monitoring known as optical stimulated luminescence OS. This material in India cannot be used because this material is developed by Western countries, and this material is little costlier for India, but Indians have develop our own material. But they have recently switched to the new technology of phosphorescence, that is luminescence. From phosphorescence to they shift to new material luminescence, and that technology is called optical stimulated luminescence dosimeter, OSLD. This is yet to introduce in India. So we must understand how this TLD material, because this is based on the reflection of X-ray beam or reflection of a incident beam albedo type, how it works, how the principle of TLD material. TLD is based on the concept of thermoluminescence. Thermoluminescence means when there is a use of thermal energy, there is a luminescence occurs. Luminescence means light. Luminescence means light. The relation between thermal energy and light, it represents a basic principle of thermoluminescence. It means that when heat is given to a material, which results in a light emission. As X-rays are nothing but a form of electromagnetic radiation, which is invisible rays, these X-rays when received by a TLD material, that TLD material contains a CaSO4 material. This material is having a material property. They have a conduction band and valence band. So what happened? Irradiation. When irradiation happens, the electrons in a valence band gets excited because of the incident radiation which is getting exposed every day, and it excited to goes to conduction band. And as I said that this TLD material is doped with dysprosium, so it has created some traps in a material. So when after electrons excited into a conduction band, they lose their energy and they fall into a trap. This trap contains your information of your received radiation. So when this material, because now your TLD is quarterly sending to a lab, all the traps in a materials is filled with some information, because you are constantly exposed to radiations, and there are so many traps have been filled. And this material when goes to the laboratory, there is a TLD reader. We can say that there is a TLD reader. This is a TLD reader. TLD reader here provides a hit to this material, and when it provides a hit to this material, the electrons which are trapped with the electrons which carry the information, the exposed radiation, amount of radiation, gets excited and enters into the conduction band and loses their energy, and coming back to a recombination center, while releasing or just switching down for it releases some amount of X-ray. It releases some amount of light. It releases light. That light is nothing but your dose. That light is converted into the dose. This is with recombination center, and the emitted light is the required dose information. Again the same picture, but the process is same. I will explain you again. A continuous exposure like irradiation excited the material, the electrons from the valence band excited to do conduction band, then they loosen their energy and fall trap into a doped material, that is a dysprosium traps, and in that traps that traps carries the information of your exposed radiation. Once when it goes to laboratory, they provides a heat because it is thermoluminescence. When you heat it, it provides luminescence, it provides a light. That light carries your dose information, and that dose information is being recorded. So how it works is, again, a receiving radiation, then release of photons, light is collected and measured, and your dose is recorded. How does it work? TLD works by storing the energy they receive from the ionizing radiation until they are heated to a high temperature around 250 degrees Celsius. There where TLD, this happens in TLD reader. On hitting, the absorbed energy is released in the form of visible light, and a plot of light intensity emitted against glow curve is known as a glow curve. So we will see what is the glow curve in our next lecture. So this is the end of today's topic. Thank you.